have been called to a meeting on Friday in Pueblo.
Ooh, lovely.
Fancy Pueblo.
We're looking at buses.
I am not sure I can arrange my kindergartner drop-off pickup. I may have to just not attend. It's a pretty important meeting. So watch your email to see whether, I'll find out tonight if I can do anything there. But
Make it to Pueblo or make it to the class?
if I make it to Pueblo, then I'll have to take the class. This is actually an important meeting for the university. The other administrative news is I'm working on the judging crew for the World Beer Cup on Monday, April 7th, and Wednesday, April 9th, which is the Monday and Wednesday after E-Days.
I feel like beer tasting could really nurse a hangover though.
Huh? Yeah, I know. I can't do the keg race this year because I'll be judging, you know. I'm actually not judging this year. I'm helping run the competition. But, I think I need to do that. The professional contacts I'll make for the school there are really good. It's looking more and more like we're getting farther and farther behind and adding more and more days. We may have to drop like the final section of the course, which is Drosophila genetics. It's very messy type of stuff. We'll do what we can with it. Okay. So, last time we left off on some lecture. What do you think it is? Oh, what? Yeah, who had a question?
So is the test going to be on Wednesday next week?
Probably Wednesday next week. That's what I guess. I have it due.
Friday.
I have it due Monday.
Monday.
We're doing mapping, right?
Yeah.
Okay, we have mapping. What do we got? Okay. So, I need you guys to pay attention to this in this class, right? You may be boring, maybe get drowsy or what like that. If you get drowsy, you just gotta really focus on this stuff. I need you to pay attention to this. This is going to be definitely one, maybe two questions on the exam, and this will be a significant part of the exam. Okay. So, last time we talked about how you can do recombination frequency. This gene and this gene have a recombination rate of 3%, so that we say those are 3 map units apart. Or, if you want to be fancy, you can say that they're 3 centimorgans apart, remember? And we talked about if I did gene A and gene B, and then gene A and gene C, and then gene B and gene C, and did each of those in a separate individual cross, we made a map up here, and that map didn't come up with numbers that worked right. And I explained that if you did a 3-point cross, if you did A, B, and C all together at one time, the numbers work out right, and it would actually be very precise. And the people, the software people and stuff who do this, when they do this type of linkage analysis and genetic mapping, they'll follow 10 genes all at one time. They know where there's 10 clear genetic markers on one particular chromosome. If they want to find some new gene on there, they can map it, almost nail it to the exact gene on the chromosome through a multi-point cross. We're only going to do a 3-point cross because that's about as complicated as I want to get into. Okay? So, let me explain to you what we've got here. For simplicity's sake, we have a pure breeding parent here, and I've made it homozygous recessive at all 3 genes, right? And this is a pure breeding line that's homozygous dominant in each of the 3 genes, right? So we cross those together, and we absolutely, for sure, must get an organism that's heterozygote at each of the 3 genes. So let me draw the chromosomes for you. At this point, I don't know if that is the correct order. V could be in the middle. B could be at the end. We will figure that out as we run this out, okay? So this organism has these chromosomes, right? If crossing over occurred in this organism here during meiosis, it had no effect. Because you trade a big B over for a big B or whatever, right? So this organism definitely inherited these two chromosomes, right? Okay. Now to do the 3-point cross, we do a test cross. Define test cross for me. A heterozygote with a homozygous recessive. This thing is heterozygous at each of these, and something that's homozygous recessive. We're not self-crossing these, right? If you, on the exam, self-cross these, you're not going to get results that you are supposed to get. And I'll be probably mean and nasty and say, I specifically told you in class. It's a test cross, okay? I'll explain why you do this in a second. So we've got that parent, let's bring in this other parent here. So as meiosis occurs in this organism, crossing over can occur. If we had a dominant gene from one of these chromosomes come in here, it might hide one of the crossing over events that occurs. We want the background that's bred in to be nothing, so we can see these chromosomes and what happened. Okay? So this is as nothing as you can get, recessive and everything. That's why you do a test cross. So you need to learn the language or the shorthand that these people use. So pay attention to this. And the video will be online. You can follow this again if you need to, right? If I have a big lab notebook and I have run, let's say I have 40 crosses that I'm running right now and this week, I'm going to write out all the crosses and score them all out. I do not want to sit there and spend 5 hours writing in my lab notebook all this type of crap. So these are all of the possible crosses that, all of the results that can possibly occur from this cross. By definition, this organism must give a recessive at everything. So since I want to be a lazy lab worker and get through my work fast so I can actually do the experiments, why on earth would I bother writing the little v? Because everybody must have a little v, because it had to come from these. And everybody had to get a little b, and everybody had to get a little p. Right? So, in an actual lab notebook, it will look almost like this. Okay? They do not even bother writing this chromosome, because it's a 0, right? It's a non-factor in this. Any questions on that? Okay. In my lab notebook, is that a capital V? Could be. Who says it's a capital V? Who says it's a little v? Okay, it's capital. Is that a little v? Yeah. Who says capital? Want to know that one? That's a little one, right? So if I have 40 crosses and I'm writing this out, I'm going to get a cramp in my hand. I'm going to get tired of writing all these stupid things out. And you may get to a point where you're like, well, that looks like a capital. And you may wind up getting to a point, or is that a V or is that a U, or trying to figure this out, right? If you're crossing a gene V with gene U with gene X, you're like, which one is which? So the person, is that a V or a U, right? So what they do, what these researchers actually do, is they write this stuff very, very carefully at the top. And then they slam the stuff out as fast as they can so they move on. And they'll screw up whether it's a big capital V or a small V. So what they can actually do is they say, if it's dominant, instead of using a capital V, I'm just going to put a plus sign there. Okay? And if it's a capital B, I'll just put a plus sign there. Anywhere the dominant is present, I'm going to put a plus sign. So that is what this means. What is the genotype of this guy?
Little b,
Little b,
big B, little b,
big B, little b, little p, little p. What is the phenotype of this one? Recessive at V, dominant at B, recessive at P. Okay? So you probably tonight will need to go home and practice understanding what this. Just walk through this, think to yourself and work yourself through it. What does this mean? What does this mean? What does this mean? Okay? Any questions on the shorthand? And the truth is, we can actually use the same shorthand on here. And the truth is, we don't even need this, and we'll get to that in a little bit. Any questions on this? Okay, so I think we can do, why do I not even need to know this up here? No, because it's not always going to be the same. I could have this as my cross.
oh, yeah, that was. But it doesn't matter. The end result's the same thing.
Look at these chromosomes.
Oh, and then.
That's you.
So the progeny of this is definitely right. This guy here is also this. Right? But it got to that point different ways, right? If no crossing over occurs, let's say we find an organism where crossing over never occurs, the progeny that come out of this cross are going to be different than the progeny that come out of this cross, right? So it turns out, crossing over, of all possible outcomes, a no crossing over event is more common than a crossing over event. So in the progeny that come out, there will be two outcomes of progeny that are huge. Those are organisms where crossing over did not occur. Which two organisms, which two groups in here, have chromosomes that are identical to the parental?
First two.
These first two. So the same, and I'll say it a couple times. If I didn't even give you this, you could tell me for sure what the parent genotypes were, because in the F2 offspring, you look for the preponderance of the parental phenotype. The number that's the biggest, those chromosomes are untainted and were unchanged in the process. They are the parental. They represent a preponderance of the parental phenotypes. That will be in every genetics textbook you would ever look at. Okay? So I'm guessing that the thing I put together here in the worksheet, I don't even give you the parents. And I say, based on these numbers, you should be able to tell me what the original parental chromosomes were. So let's go backwards. I mean, we have the parental chromosomes up here, but just looking at these numbers, I could say the original parental chromosome was this. From this, and this guy must have been right? We'll get to another example, we'll test you on this again. Okay. So, this is what we've got. These are the original parentals. No crossing over occurred there. We don't even need to look at these numbers. We can just throw these numbers away. What we want to know is how often did crossing over happen between these two genes here. So if this is the parental, a crossing over between these two genes would put a little b over here and the capital B over here, right? Let's not worry about p at this time, right? In our shorthand, what is the shorthand writing for this?
Plus B.
This chromosome is what?
Plus B.
Plus little b. What's the shorthand for this guy?
Plus.
Little v, yeah, plus. You guys understand that? So what I want to do is I want to look at the outcomes and say, anytime I find a plus and a little b, that was a crossing over event that happened between these. So for between genes V and B, if I find a plus and a b, there's one, there's one, just the two, plus and a b. 252 and 131. Crossing over happened there. Out of that many progeny, out of 4,000 progeny, those and those had a crossing over event. And anywhere there's a little v and a positive, there, just those two. 241. What was the other one? 118. Out of all of the chromosomes from all the organisms, it's only these organisms here where we had a crossing over event. So I'm going to add all these up. Does everyone understand why I know those are crossing over events? Because those chromosomes don't look like the parent, right? This is the parent chromosome, or negative, or little, right? Any questions on that? Okay, so I add these up. I've done that right here. 742 organisms out of, if you add all these numbers up, 4,197 organisms. That can give us a percent of the organisms where crossing over happened between the genes V and the gene B. 17.7%. These genes are 17.7 map units apart. It doesn't tell you how many nucleotides that is. We don't know. It's map units apart. Everyone got that? Okay. I want you individually to go and tell me how many map units, what's the recombination frequency between V and P, and then I want you to tell me the recombination frequency between B and P. still working? A couple people? It's hard to keep it straight, isn't it? I'll put a bunch on these in. Right, who's still working? Anyone still working? Okay. You guys come up with the same numbers I did? So I've been teaching this class for 9 years, 8 years. Maybe my ninth time teaching this, I suppose. I still write out, okay, these are the genes I'm comparing. I still need to write out, this is what I'm looking for. These two things are what I'm looking for. And then I write the numbers down and I can add them up that way. Does that make sense? Okay. So, let me show you a neat little trick. Once I determine those guys, I can go like this. $252, $241, $131, $118. 241, 13, 252, 9. These guys are all done because I've used them twice, which means all I need is 131, 118, 13, and 9. Everybody gets used twice. So I don't rely on that. I do it the long way, and then I go back and double check. If I've used 13 and 9 once each, I screwed up somewhere. It's my double check. Does that make sense? Every one of these guys has now been used twice. Questions on that? Okay, so let's see if we got these right. Looks like I got that one right. 515 divided by basically 4,200, that gives us 13.2.
12.3.
Sorry, what did I say?
13.2.
Dyslexic today. How? 12.3. And then for the other one, got that right? That is 6.4. So let's draw a map. Let's map these guys out.
So you said those percentages are the respective map units?
That's it, yeah. You can call it 12.3 RF, recombination frequency, 12.3 map units, or 12.3 centimorgans if you want to watch me finish. Okay? So let's map these out. Which two genes are the farthest apart?
B and B.
Yeah, B and B. Right? So that means P is in the middle. Is it exactly in the middle? No. Where's P? Closer to B? Okay, so if this is 17.7 map units, this is 12.3 map units, and this is 6.4 map units. It should be accurate and we should nail it, right? I told you this is exactly precise. If we go 12.3 plus 6.4, we get 18.7. Oops, what the hell happened? the arithmetic and division is correct.
Large enough sample size, maybe?
Nope, doesn't matter the sample size.
Maybe because we're not taking into account like non-crossing.
No, non-crossing over doesn't factor into this. That's a great guess though. And you're kind of on the track, right track.
Does one just take up a lot of room? You kind of just say that.
Oh, that's
It
interesting.
takes up a whole
Just
unit.
does the length of the gene matter? I think not.
Okay.
That was a very clever guess though, I like that. But,
What about if it crosses over and crosses back?
oh, double recombination event. Check this out. Check this out. Let me show you the chromosome. Let me draw it over here. So in our recombination frequency between V and P, these guys are the farthest apart? Is that what we did? Oh, so the chromosome, I guessed incorrectly when I drew this up here. Okay, so it's actually like that, right? That's the actual, these are the actual chromosomes. What if we cross over like this? Did I draw backwards again? Right? And crossing over happened again. Crossing over happened twice, but in this set. Crossing over happened in this spot between here. It happened this. It happened at this spot, and then it happened at that spot again. But we didn't count it because phenotypically, this guy looks like it didn't ever cross over with this. We don't see that in here, right? If we had plus, plus, or this, we said that was parental, we didn't count it, right? So in these numbers are actually the double crossover guys. In the same way that the parental is the most common offspring, go back here. These guys have the parental chromosomes, the preponderance of the parental rate. The chromosomes have not had any crossover events, that's why these are the largest. Because crossing over is going to be a rare event. Double crossing over is really, really, really uncommon. Which ones do you think were the double crossover events?
The 9 and the 13.
The 9 and the 13. V and B stayed together, but the middle one swapped out. This is this chromosome. Yeah.
When you say parental, do you mean the F1, the
Yeah,
parent
these
or
guys
the
up here,
background? Okay.
Yeah.
So for like the shorthand notation, so obviously, so we're saying like the first use of the BBP and the plus 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 are the parents. So within the F2, the plus 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 means that they're heterozygotes.
Yes.
the B,
Because
but-
they had to get this from over.
Yeah, but when you're looking at that to predict the parents, you just know that they're homozygous.
I'll really mix it up now.
Okay.
I'll really mix it up for you in a second. This is the simplest possible example I could do one of these. I'm going to give you one, I'm going to make numbers up, I'm going to give you a really hard one and show you how challenging it really can get. If I passed out. Phone passed out. Okay. So, how do we score the double recombinants? How do we factor those guys in? Yeah, we need to add these guys on. So we need to add a 13 and a 9 and a 13, and a 9. You had a double cross on it. You added on twice. And I'm blanking now on why you added twice. I had a really good explanation for it.
Just trust you.
No, I'll have it next time we meet.
Okay. For now, trust
Okay. If I add these on, now this number goes up. What number do you think it goes up to? 18.7.
So do you always, whichever one's like the greatest and isn't included in that one, add the other two twice?
Say that again?
So like always do you, whichever, like so the B and the B have the greatest difference?
Yes.
Do you add the other two that weren't included, so 13 and 9 twice, like in
Yeah,
any
no,
situation?
Yeah, yes, exactly.
Okay,
Right, right, right.
so it follows a general pattern of, okay, this is the greatest separation and these two numbers weren't involved in it, added twice.
Yes.
Okay.
Yep. Very good. So let me walk you through that. So those guys need to now be added onto this. So I'm going to move this over here and add these guys on. And you figure that number out and it's 18.7. Correct? Okay. Questions, comments? Okay, let me give you let me make up an example here. Right? I'm going to do this in color actually. Right? Right? So in shorthand, this guy is actually work. Right? On the exam, what you're going to get is this. Right? Let me draw the chromosomes. And I don't know if this is the correct order or not. Okay. So then I bring in test cross, read these guys out. What are the parental chromosomes? How would I shorthand notate the parental chromosomes? Plus, little b plus. What's the other parental chromosome? Little a plus little c. So let's say this is 1,000, 1,000. So the recombinants will be wow, I'm missing one in here now.
Plus little b plus.
So let me do this. If I had a crossing over between A and B, gene A and B, what that would look like is a big A would now match up with a big B. Right? Shorthand, that is what? And the other possibility is, if I have crossing over between A and C, this A now must get matched up with a little c if crossing over occurred, right? So big A matched up with a little c, or what's the opposite? If I have crossing over between B and C, my little b should now match up with the what? Little c. Does that make sense? So the last time it was easy. Let me draw for you what happened last time. That was the parental. And that was the parental. Right? So if you had an A with a not with a, so if you had a plus with a letter, you knew that was a crossing over, right? But because I've got the parentals different, now you have to track that. You see how it mixes up things up? It gets hard to keep the stuff straight. So that's why I draw this out this way every time. So between A and B, if I have a plus plus, it's a recombinant. 200 and 150. An A and a B is going to be 200 and 150. A plus and a C plus and a C, there is 200. Plus and a C, 50. Right? An A and a plus. A and a plus here, 200. A and a plus here, 50. So I need a 150, 150, 50, 50. I should do it that way. I'm lazy and I'm running out of time. Does that make sense? These numbers, which two genes are farthest apart?
A and B.
A and B, yeah.
Could we go ahead and already add the 50 times 2 to the A and B, since we know those are the double?
So they're the farthest apart. The double recombinant must be in that group. Which are the double recombinants?
The 250.
That's 1, and that's 2. You do it twice, right?
Will you get crosses just by random chance that you won't get like any double crossing over? Or is this just something that is sort of always present?
So your question is, are there crosses you can set up where you get no double crossing over
Or just by
events?
chance?
Just by chance. I mean, if you have a large population, you get double crossover events.
You just will.
Yes. Unless the genes are like in less than one map unit. If you have all your genes in less than one map unit, you may not get crossover events in between. Okay? This is hard, isn't it?
How many do they do this for sometimes? Like the maximum number?
Oh, they'll do 10 genes, no problem.
Saw 7.
There are computer programs where they don't do it on paper now.
Okay.
There are computer programs. You type in the numbers and it spits it all out. It gives you the map and exactly pictures. But students at the school mines have the amazing opportunity to do it by hand. Okay? So there is, in your worksheet, there is one of these in the back page. And it's a hard one. It's something like this. frequency crossing like that. And I don't tell you what the parentals are. I give you these numbers, and you need to figure out which of the parentals are. The big numbers. The double crossovers or the small numbers. So people who do this a lot, they run through this pattern. It took us an hour to run through one example, right? And then, we had 5 minutes, we just ran through this real quick. People who do this all day, every day, they will get these numbers, and they can, just from these numbers, looking at the numbers, they know which are the farthest apart, which is a double crossover, and they can kind of map it out real quick that way. Just looking at these numbers, they know it will be. So they've just done it so much as routine. Yeah.
If those bottom two were, instead of 50, like 125, since it wouldn't be that big of a difference, like clearly it's a small number.
That's a great
We could
question.
just assume there was no double crossing over?
No, no.
Or would we say the 125 and 150 or whatever we're crossing over?
So the question is, what if these are 125, very close to this number? What that means, if you work the numbers out, you can do that. Everybody has a homework assignment. I'm just kidding. I'll answer that question on Monday. Because we're probably not meeting on Friday.
Okay.
I'll answer, if you want to know ahead of them, figure this out. Make your double recombinant a number very close to this. Make it 50, and then make this number 125, so it's really close. Map it out, and then you will know what the difference is, and you'll be able to explain it. That's a great offer. That's next year. That will be a homework assignment.
Well,